Hello, is it audible?
Yes, sir.
Okay. Today we are going to discuss about Newton's law of viscosity. Newton's law of viscosity. If the fluid follows this law, then the fluid is called as Newtonian fluid. If any fluid follows Newton's law of viscosity, then that fluid is called as Newtonian fluid. So then, what the Newton's law of viscosity states? According to Newton's law of viscosity, it states that at any point in the fluid, the shearing stress at any point in the fluid, the shearing stress is directly proportional to rate of shear or velocity gradient. So, any point in the fluid film, the shearing stress is directly proportional to rate of shear or velocity gradient. For this, uh, we made some of the assumptions. The first assumption is there is no vertical load applied to the surface. There is no vertical load applied to the surface. Means no load is acting. There is no vertical load acting on the surface. Load is zero without load. Second is the oil is incompressible. The second important assumption is oil is incompressible. Means we cannot compress the oil. It is not compressing. It is incompressible. Then only it will maintain the pressure. If it is compressible, means there is it won't maintain the pressure. That's why it is incompressible. Next assumption, the adhesion between the lubricant and the surface is perfect. Means adhesion between the surface and the lubricant. It may be bottom surface or top surface. So there is a perfect adhesion between the top layer of the lubricant and the surface. There is a perfect adhesion between top layer of the liquid or bottom layer of the liquid to the surface. Then only it will transmit the velocity. So next assumption, upper surface is moving with the same velocity. Means whatever the upper surface of the lubricant is moving with the same velocity of the moving surface. Whatever the moving surface is having the velocity u, the same velocity is having the upper surface of the lubricant. So these are the four important assumptions what we made for this Newton's law of viscosity. Okay, and this is the typical figure. Here you can observe that the first whatever see this plate is a moving surface. This plate is a moving surface with a velocity of u, and it is applied with a force F. Force F is applied on this plate so that it is moving with velocity of u, and this surface is stationary surface. This surface is called as stationary surface, and here it is an velocity is zero, means it won't move. It is a stationary surface. The top surface, top plate is velocity u with a maximum velocity u, and bottom is stationary surface. It is of zero velocity. In between these two, it is completely filled by fluid film. Completely filled by fluid film, and this fluid film is having a layers. Here you can observe that. So this is what the layer of fluid film. and this top layer it is an moving with the same velocity u, and the bottom this layer it is an velocity 0, because there is a perfect adhesion between this surface and this layer, so that velocity is 0. Here there is a perfect adhesion between this moving surface and this top layer, so that it is having also same velocity u. So in between these two it will different, means velocity is maximum to minimum, it will vary. Top layer is maximum u and bottom layer is 0. In between maximum minimum it will vary. Okay, here you can see this is the maximum velocity and minimum velocity, these are the layers of fluid film. Okay, and this is what h is the gap between this moving plate and stationary plate, or the thickness of fluid film, whatever it may be. Okay, and dy is a small the thickness of a small one layer of fluid film, and du is the what the displacement because of this moving plate. Du is the displacement or a velocity of a small change in velocity with a small layer, that is dy. Here you just consider a element of this oil in this fluid film whose cross section at this instant is outlined by rectangle A, B, C and D. Consider an element of oil in this fluid film whose cross section at this instant is outlined by rectangle A, B, C, D. After some time, it will be changed due to the flow in due to the flow or due to the force or due to the flow. There is a change in ABCD to a new position a dash, B dash, C dash and D dash. This displacement of each point is proportional to the distance from the stationary surface. Means this displacement A to A dash is more when compared to C to C dash. B to B dash is more compared to D to D dash. It is just due to because of it is proportional to the stationary surface. Means this proportionality is same. Means if keep on moving to the bottom surface or stationary surface, this displacement become 0 and it is maximum at the top surface. Okay, and, and this can be written as that we can write it as R, so R is equal to du by dy, du by dy, that is R is rate of shear or velocity gradient. This R is called as rate of shear. It is called as rate of shear or velocity gradient. This is for a small layer. If the rate of shear in this oil film is constant, a value for any point in the fluid film, it is become, then we can write it as R is equal to U by H, U by H, where R is the rate of shear, U is the velocity and H is the thickness of the fluid film or gap between moving plate and stationary plate. According to Newton's law of viscosity, we know that shear stress is directly proportional to rate of shear. Shear stress is directly proportional to rate of shear. Then this proportionality constant we can replace it by mu into R. Mu is the what we call as mu is the constant of proportionality. Mu is a constant of proportionality. Then we know that we can write it as mu is equal to tau by r. Okay. Then the same mu, where tau, we already know that tau means shear stress. Shear stress means it is an force by area. F by A whole divided by R means we already know that U by H. That we can write it as mu is equal to FH by mu A, where area is constant and height is 1 meter, then velocity is 1, means everything is constant, then mu is directly proportional to or equal to force. Okay, where u is the proportionality constant and F is the force which is applied on the plate. Okay, so this is what we can call it as a Newton's law of viscosity. And this mu is proportionality constant. Here you can see this is r du by dy velocity gradient, and where r is equal to u by h. U means velocity, h means thickness. According to Newton's law, tau is proportional to rate of shear, that is tau is equal to mu into r. That is this unit of this mu, that is what absolute viscosity, is equal to poise. It is in terms of poise, Newton per meter square second. Okay, so this is a small derivation, and after this we move on to the next important derivation. Means most probably you're going to get in your examination. It's a very important derivation. This derivation is also called as Huygens-Poiseuille law, or it is also called as equation for flow of liquid through a capillary tube. A flow for a it's a equation for a flow of a liquid or fluid through a capillary tube, or it is simply called as a Huygens-Poiseuille law. Simply it is called as a Huygens-Poiseuille law. Here it is a capillary tube. Okay, this is a capillary tube. It's a front view and a side view. It's a side view and front view. This bigger circle is a capillary diameter. Okay, and a small circle, it's an imaginary element. And this is a length of capillary tube, and this is a length of imaginary element. This is how the parabolic distribution of pressure, how the pressure is distributing along or through the capillary tube. It is minimum at the top surfaces or bottom surface because it is a stationary, and it is maximum at the center. The velocity is maximum at the center and minimum at the surfaces, bottom surface or a top surface. Minimum to maximum it is varying, and this variation is parabolic variation. Here Huygens-Poiseuille discovered the relation between a rate of flow of a liquid through the capillary and the other factor such as a viscosity of the liquid, diameter of the capillary tube, length of the capillary tube, and the pressure. Means a Huygens-Poiseuille discovered the relationship between a flow through capillary along with some of the factors like viscosity of this fluid, the diameter of the capillary, length of the capillary, okay, and pressure. within the capillary tube. Consider an equilibrium force acting on a cylindrical element. This is a cylindrical element. Consider a small cylindrical element. Okay, on this element, okay, consider a equilibrium force acting, means the equilibrium force acting on this a cylindrical element of a liquid or a fluid having radius small r, having radius small r and the length dx. This is the length dx which is shown in the figure. Okay, consider a small imaginary element which is in the same like a capillary. Okay, a small capillary element, if it is having a small radius r, small r is the radius of that imaginary element, dx is the length of the imaginary element, and it is at equilibrium position. Equilibrium means all the forces are equal, right hand side force equal to left hand side, top force equal to bottom force. That is what equilibrium. Assume that the pressure at the left capillary tube is higher than the right end. Then the pressure drops gradually along the tube from the left to right. The pressure causes the fluid to flow in the direction from left to right. Here you have to assume that the left side force is more than a right side force, so that the fluid is flowing from left to right. And some of the other assumptions are the flow is steady and laminar flow. Some of the other assumptions in the derivations are the flow is steady and laminar flow. It's an incompressible fluid and completely filled with the bore of tube, means it is completely filled of bore of the tube, capillary tube. The diameter of the capillary is so small, the change in the pressure across the capillary can be neglected. Means here the diameter of the capillary is very small, so that change in the pressure across the capillary is neglected. Across the capillary it is neglected. Okay, so first the pressure, come to the pressure ports on the left hand face of the element is, the pressure ports on the left hand element is P. We know that force means pressure into area. So P is the pressure, area means this area, the area of this face, small imaginary element area means pi r square, the circumference, the pi r square, pi r square. So area into P, that is pressure. So pressure into area, it gives the force. Whatever the force acting on the left hand, left face is P pi r square. Similarly, the pressure force along the right face, it is equal to the same pressure, but the pressure is very less. We know that right side compared to left side. So that P minus dP. Minus dP is the small change in pressure. A small change in the pressure. So that is P minus dP, and the area is same. Okay, pi r square. The pressure on the right hand side, P minus dP pi r square. Okay, two force. Next, one more force, shear force. Okay, the shear force on the element, the shear force on the element, the shear force. This is a small imaginary element. On this element, there is a shear force acting. So that force we can tau. So shear stress tau into area. Stress into area, that gives the force. Okay, tau is the shear stress into area. Area of this element, it is 2 pi r is the circumference along the length dx. So 2 pi r into dx, that gives the circumference into length, that gives the area, that area into tau, it gives the force, that is shear force. And we already know that it is in the equilibrium equation, so that we have to equate all the values, means according to their directions. So here there is a positive, it is towards the right side. This is negative because it is in the left side, and it is also negative because it is left side. So that equating to 0 p pi r square minus p minus dp into pi r square minus tau 2 pi r into dx, equating to equilibrium equation. So now just rearrange this, expand so that pi r square get cancelled. dp pi r square minus tau 2 pi r into dx. Here just take out the common factors and multiply into the left side, that is right side, that is 0. So here pi is common and r is common. You just equate to 0, means it is become 0. Multiply to 0, it is become 0. So dp r minus tau 2 dx is equal to 0. Just rearrange. If you rearrange, it is become dp by dx is equal to 2 tau by r. Okay, call it as a equation 2. According to Newton's law of viscosity, we already know that according to Newton's law of viscosity, tau is equal to mu into r, where r is the velocity gradient, that is r is equal to du by dr. It is for small element. Okay, same thing, if you replace here, tau is equal to minus mu du by dr. Why I write minus means, the negative indicates that velocity of the liquid decreases when r increases. See here, the velocity of the fluid decreases when r increases. If you increase the r from 0 to capital R, the velocity decreases. This decrease in the velocity indicated by negative sign. Okay, call it as a equation 3. Now substitute equation 3 in 2. Substitute equation 3 in 2. 3 into dp by dx is equal to, in the place of tau, you just write in the place of tau, minus 2 by r mu du by dr. And if you just rearrange, minus r by 2 mu dp by dx is equal to du by gr, where just multiply this r to left side, it is become du is equal to, we need a velocity, so separate the du term. Du is equal to minus r by 2 mu dr dp by dx. Integrate this equation 4. You just call it as equation 4 and integrate this equation, you will get velocity. Du integrate, here 1 by 2 mu dp by dx is a constant, and r into dr, we know that integration of r is equal to r square by 2 plus c is the integration constant. You have to find out the value of c, then you have to substitute, because you have to find out the integration constant. How you are going to find out means, by applying the limits or boundary conditions. When the velocity is maximum, when the velocity is minimum. The boundary conditions are, where small r is equal to r, velocity is 0. We already know that when the small r is 0, the velocity is maximum. Velocity is maximum, umax. When the small r is capital R, velocity is 0. These two are the boundary conditions. Small r is equal to capital R, velocity maximum u, where small r is equal to capital R, velocity is 0. The same boundary condition we have to use here. See, when small r is equal to capital R, velocity is 0, first boundary condition. Similarly, second boundary conditions, when small r is equal to 0, velocity is u. By apply these two, same thing, apply them here, and you will get the value of c. Substituting c value in the equation, you will get u is equal to 1 minus 2 mu dp by dx r square by 2 plus 1, the same, the value of c, substitute here, 1 by 2 mu dp by dx r square by 2. And here just take out the common, 1 by 2 mu dp by dx, 1 by 2 mu, here also 2, so 2 into 2 4, it is become 1 by 4 mu dp by dx r square minus capital R square minus small r square. This is the velocity distribution for this capillary tube. Okay, the velocity distribution is a parabolic in nature. We already know that the velocity distribution is parabolic in nature. So u max is, velocity is maximum when small r is 0. So velocity is maximum when small r is 0. That is the maximum velocity what we are getting in the capillary tube. And always capillary tube, the velocity is maximum at the center and it is minimum 0 at the capillary tube surface. Okay, and finally we need a we need flow rate. We already got the value of velocity, but we need a flow rate. The maximum velocity appears on the axis of the capillary tube using the velocity distribution. The rate of flow through the capillary can be estimated. This can be done by integrating on the velocity over the across the cross section of the capillary. Since the product of area and the fluid velocity is equal to rate of flow, we need a rate of flow. That rate of flow is equal to velocity into the area of the fluid. It gives the what? It gives the, yes, flow rate. The flow rate du is equal to dA into u. U is the velocity, dA is the area. Here also same thing, we have to consider a small element, okay, through which the fluid is flowing. So it is a capillary, so that we have to consider a circular element, and this is a side view and this is a front view through which it is flowing. Let us u be the velocity of the element of the ring and dA is the area, where dA is 2 pi r into dr. So 2 pi r is the circumference and dr is the thickness. So dr into circumference, it gives the area of the imaginary element. Okay, so that dq is equal to 2 pi r dr into u, that is area into velocity. Okay, and here u already we got the value, u just previous only we got the value u, equation 7, same substitute here. So dq is equal to pi by 2 mu dp by dx r square minus small r square into r into dr. So the flow rate, if you want to flow rate, you have to integrate. So if you integrate dq, it is become q, that is flow rate, and again you have to apply integration for right hand side also. So if you apply the integration with respect to the limits 0 to r, 0 is the small r 0 and small r is equal to capital R, means velocity is maximum to minimum, here 0 to r. So integration dq is equal to pi by 2 mu dp by dx, here 0 to r integration r square minus small r square into dr r into dr. Here, if you integrate, it is become q and take out the common, pi by 2 mu dp by dx. If you integrate, okay, so r square is constant here, r into capital R square. So small r means integrate, it is r square by 2, and here small r square into small r, it is become r cube. If you integrate r cube, it is become r to the power of 4 by divided by 4, and limit 0 to r. If you substitute this value 0 and r, now it is simplified to capital R square by 2 minus capital R square by 4. And if you simplify, take the LCM and simplify, the final equation is q is equal to pi by this 4 into 2, it is become 8 mu dp by dx into capital R square. This is the Eigen-Poiseuille equation or a flow through the capillary. Both are same, Eigen-Poiseuille equation or flow through the capillary. This is how we got the value of q, flow rate. First you have to find out the u, velocity, then by using velocity into area, it gives the flow rate. Okay, this is an important derivation. In the exam you may got the same question like this. Derive equation for flow of liquid through the capillary tube or derive Eigen-Poiseuille law. First you have to write this figure and explain, then consider all the forces on right side, left side as well as on the element, then equating into the equilibrium equation and simplify and use the Newton's law of viscosity, because the fluid is following Newton's law, and use this equation and substitute and rearrange, then integrate, you will get the velocity equation. Here it is a c is the constant. To remove this integration constant, you have to apply the limits, and finally you got the value of u. And once you got the value of u, again consider the same imaginary element of that velocity u, and with the area a, if you multiply velocity into area, it gives the flow rate. And this is equation, and after integration by using the boundary conditions, we will get the Eigen-Poiseuille law. Q is equal to pi by 8 mu dp by dx into capital R to the power of 4. It is called Eigen-Poiseuille law.